Hi everyone. So in this video I'm going to share with you one problem that came up in numerous software engineering interviews for companies such as Google, Microsoft, Apple, and even Dropbox a while back. However, rather than just jumping straight to the solution, I'll try to slowly walk you through the solution and potentially how you might have came up with the solution yourself, or in other words, the intuition behind the solution. So here's the problem. Given two sorted arrays, array A and array B, of sizes m and n respectively, find the median of the two sorted arrays. Now, take a minute to digest the question. Some questions which might pop up in your head are, what is a median? But more importantly is, how do you even approach this problem? Where do you even start? So let's start with the obvious question. What is a median and how do you calculate the median for a group of numbers? Well, calculating the median for a group of numbers depends whether there's an even number of numbers or an odd number of numbers. So let's start with the easier version. Suppose we have an odd number of numbers, such as the case here where we have 9 numbers. Then, to find the median element, we first sort these numbers in ascending order. Next, we want to find the element in the middle. In this case, it's the fifth element, since the fifth element, which is 5 in this case, has 4 numbers bigger than or equal to it, and 4 numbers less than or equal to it. And since it's the middle element, it's the median. In general, if n is odd, then the n plus 1 over 2th element in the sorted order of the numbers is the median. We can also reword this as saying that the n plus 1 over 2th smallest element of the numbers is the median. When there's an even number of elements on the other hand, then finding the median isn't as straightforward. In this case, you'll still have to sort the numbers first. But in this case, you would notice that there isn't really any middle element. The middle element seems to be this line over here, dividing the elements into two sides with equal number of numbers on each side. 4 on each side in this case. So, in the even case, what we do is select the two elements touching the middle line and take their average to be the median. So, in this case, the median will be 4 plus 5 over 2, which is 4.5. In general, however, if n is even, then the average of the n over 2th and the n plus 2 over 2th elements in the sorted order is the median. This can similarly be reworded so that the median of n even numbers is the average of the n over 2th and the n plus 2 over 2th smallest elements. Great! So we've established what medians are, and how we can calculate them for a group of numbers, whether it's an even number or an odd number. So let's go back to our problem and see what it's really asking for. Given two sorted arrays A and B of sizes m and n respectively, find the median of the two sorted arrays. So let's try to visualize this by taking an example. Suppose that A is a sorted array of 5 numbers, 1, 4, 5, 6, 8, and that B is another sorted array of 3 numbers, 2, 3, 7. Now, the problem is asking us to calculate the median of the numbers in both of these arrays. Note that we want the median of the union of the numbers in both of the arrays and not the individual median in each array. Take a minute and think how we can achieve this. Try to find the simplest way we can solve this, no matter the complexity of your algorithm. Remember that Donald Knuth, a great mathematician and computer scientist, said that premature optimization is the root of all evil. So for now, focus on finding a simple solution. one that works, and forget about big O notation and all that stuff. So, a simple idea that you might get is to use the definition of the median. Namely, we will combine A and B into a new array, say C, and then we will sort array C, then find the median of C as we usually do. So in this case, the median would be 4.5 again. And this is indeed a solution, but there's a couple of things that don't feel quite right. Let's go back to the problem statement. Given two sorted arrays, A and B, of sizes m and n respectively, find the median of the two sorted arrays. Now, we've indeed found the median of the two sorted arrays, but in this case, we haven't really used the fact that A and B are sorted anywhere in our solution. In fact, if we go back to our solution and take any two arrays, A and B, that are not necessarily sorted, so for example, A equals 1, 5, 4, 6, 8, and B equals 7, 3, 2, then we can concatenate the two arrays into C, then sort C, then find the median, which in this case is, as expected, 4.5. Something seems a bit off here. It seems like the fact that the two arrays A and B are sorted isn't really important in our algorithm, since regardless of whether A and B are sorted or not, the algorithm sorts them once they're added to C. Can we use the fact that A and B are sorted to somehow make this process a bit faster? Take a minute and think how we can sort A and B into a sorted array without having to put them first into one bigger array and then sorting it. Try to use the fact that A and B are both sorted to merge them into one sorted array, C. So let's imagine we start at the beginning of array C. We want to fill in C such that the elements are inserted in ascending order. So let's start with the smallest element in C. Which elements might be the smallest elements in both A and B? Well, the smallest element in A and B is either the smallest element in A or the smallest element in B. This is because all the other elements in A are going to be bigger than the smallest element in A, and all the elements in B are going to be bigger than the smallest element in B, since again, A and B are in their ascending order. So, in this case, the smallest number is the first number in A, and hence we take it. Next, we want the second smallest element in C. Since we already got rid of 1, we can move the pointer in A one step forward, as there's currently no elements in A in the first index. Now, the second smallest element can either be the smallest number of the numbers left in A or the smallest number of the numbers left in B, because all other numbers in A and B are larger than these two numbers. In this case, the smaller number is 2, so we choose 2 as the second smallest number inside C. We can repeat this process until we have constructed the sorted array C from scratch. This is much more efficient than constructing the array C first and then sorting the whole array. Instead, we use the property that A and B were both originally sorted to generate a sorted array C. Then, finding the median should be straightforward like we did earlier in the video. The median in this case would be 4 plus 5 over 2, which is equal to 4.5. Now, to quickly recap what we did, we first started with the definition of what a median is, and used it to come up with an algorithm for finding the median. We then noticed this algorithm was too general and worked for any arrays, sorted or not. We established that the sorting step was the bottleneck of the algorithm and came up with a better way to generate C from the two sorted arrays A and B. Now, this is good and all, But if this was everything to learn about this problem, then I wouldn't really be making a video on it. See, this is an excellent example of a problem that can be solved efficiently using a problem-solving technique called variation of the problem. Now, variation of the problem is an extremely valuable problem-solving heuristic that was explained in Polya's book, How to Solve It, which is an amazing book about problem-solving. Now, this technique appears frequently in math, computer science, and sciences in general, as it's a surprisingly powerful problem-solving technique. Now, this technique needs a slight mental shift in the way that you perceive problems, and although oftentimes you might see solutions to problems that seem so creative and out of your reach, oftentimes than not they're actually implementations of this technique. Now, the technique, put simply, asks, can you vary or change your problem to create a new problem whose solution will help you solve the original problem? Sounds too obvious, right? However, you'd be surprised how strong this heuristic is in solving problems, as we'll show in this video. The heuristic essentially asks us to try and modify the problem into something else, something that we can solve, and whose solution would help us in solving the original problem. That's easier said than done. Now, let's try to remember our problem. We have two sorted arrays, A and B, of sizes m and n respectively. How can we find the median element? Can you try and apply the variation of the problem technique here to find a solution? See, all this time we've been so busy trying to identify that median element, looking and looking for it, while neglecting all other numbers. Can we somehow transform our problem to focus on these lonely numbers? Can we perhaps focus on something other than the median? But I hear you. What else in here is interesting? I mean, surely we only care about whether this element is the median or not the median. Or not the median. We're finding that it's too hard to find which element is the median of the two sorted arrays. What about elements which are not medians? I mean, if there are m plus n elements, then surely only one or two of them are related to the value of the median, and all the others are non-medians, right? But if this is the case, then wouldn't it be easier to just look for non-medians and get rid of them? And just like that, we've applied the variation of the problem technique. Rather than trying to find that special median element, we'll instead try to get rid of all the elements which are impossible to be medians. So we can reword our problem as, given two sorted arrays A and B of size m and n respectively, find the numbers which are not medians of the two sorted arrays. If we could find these numbers, then we can just delete them, and whatever is left is the actual median. Now, take a minute to digest this. See, this subtle change in perspective from searching for something to searching for the opposite of that thing and removing it in the hopes of leaving what you want is a classical example on the variation of the problem technique in action. And this subtle change in perspective will prove extremely useful in the coming few minutes. Now, let's go back to our A and B arrays. We already mentioned that at most one or two elements from the array will be involved in finding the median, and the remaining majority of elements will all be removed. So, since we're looking to delete all the non-median related elements, and they are the majority, rather than removing one element at a time, let's try to get rid of a big chunk of A and B at every step to try and speed this elimination process. Now, a couple of questions which might pop up in your head, such as how big a chunk should be and should the chunks be fixed size or not. Now, in this case, since the problem involves so much with dealing with the median, my intuition just tells me that we should chunk every array into two parts. However, remember, this is just a hunch and intuition and could very well be wrong, which it could be a valuable part of the problem-solving process. So let's go ahead as planned and split the arrays A and B into two chunks. Now, notice that A has an odd number of elements, and so we can't split it exactly into two halves, and that's okay. When one of the arrays is odd, we'll allow one of its chunks to have at most one extra element. Now, remember, our main goal is to decide whether one of these chunks can be let go. But remember, each of these chunks has numbers in it, so we need to find some sort of way, or representation, to describe what each of these chunks represent. Also, since we decided to split each array into two chunks, it might be useful to consider the pivot or central value of each array for reference. So I'll call 4 the central pivot of A and 3 to be the central pivot of B. Notice that these two pivots are not exactly special in any way. I could have chosen 5 and 7, or 4 and 7, or even 5 and 3. The important thing is to be consistent throughout your notation and your choice of later pivots so you don't confuse yourself. Alright, back to the problem. We're trying to somehow remove one of these chunks at every turn, since the chunk will contain elements which are not medians of the two arrays. Notice, however, that we don't have the ability to look at every element inside each chunk to decide whether to remove it or not, because that would be the same as the merging solution that looks at each element once and sorts it in order. So somehow, using some way, we need to get rid of a chunk by looking at as few elements as possible. If you spend some time thinking about this problem, then you would eventually reach a conclusion of why the central pivot idea is very strong. See, since we know that the original A and B arrays are sorted, we know that the elements to the right of the pivot A must be greater than or equal to the pivot of A, and similarly all the elements to the left of the pivot of A must be less than or equal to the pivot of A. We can also say a similar thing about B. Now, take a minute to digest this, because this is very important. By just being able to peek at the value of the central pivot, we're able to know a lot of information about the two chunks. See, imagine you didn't know the numbers in A and B. You only knew the values of the pivot. What can you tell me about the chunks of A and B in this case? We can see that in A, all the elements to the right of the pivot of A, which is 4 in this case, are greater than or equal to 4, and the ones to the left are less than or equal to 4. We can say a similar assertion for B too. We said that we want to remove one of these 4 chunks which has elements which are not medians. Now, since I know the length of A and B is m and n respectively, then I know that the length of C is m plus n. Also, I know that if m plus n is odd, then I'm just searching for the m plus n plus 1 over 2th element in the sorted order of C, as we mentioned earlier. If m plus n is even, however, then we're searching for both the m plus n over 2 and m plus n plus 2 over 2th element in the sorted order. So really, finding the median boils down to being able to find the kth element of the sorted array C, where k is m plus n plus 1 over 2 if m plus n is odd, and k equals m plus n over 2 and m plus n plus 2 over 2 if m plus n is even. This is another application of the variation of the problem technique. Great, we're finally ready to sum all of this up. Our objective is to find the kth element in the sorted order of both arrays. If we're able to write a function, an algorithm of some sort, to get the kth element in the sorted order of A and B, then we're essentially done. we're just gonna use this function to get the median of C. But we go back again to how would we go about writing this function or algorithm? Well, for starters, let's give it a name. Let's say get kth element in sorted order. Now, this function is basically going to get the kth element in arrays A and B. So we need 3 arguments here, namely A, B, and K. And our function should return that kth element in the sorted order. So before discussing the general algorithm, why not just handle some of the corner cases? For example, if A has no elements, or equivalently if m is equal to 0, then the kth element in the sorted order is just the kth element in B. Similarly for B, if it doesn't have any elements, then the kth element of A is the kth element in the sorted order. So that's easy enough. Now, what happens if both A and B have elements? Now, during problem solving, it's often convenient to consider different cases and how you'd handle each cases, and then in the end, you can combine all cases for just one algorithm. This is also known as divide and conquer. So in this case, if you spend enough time on the problem, you might come up with 2 cases. Namely that the number of elements on the left chunks are bigger than or equal to k, or that they are less than k. Here, the function pivot of A tells me that the index of the pivot of A, so in this case, pivot of A is equal to 2, because the pivot is the second element, and pivot of B is also 2. Now, the intuition behind this is that you want to know whether k is after the middle of the sorted array or before the middle. Well, first of all, we don't know anything about the elements in A and B, so for now, to get some information, we're going to peek on both the pivots of A and B, and in this case, they were 3 and 4. However, that's not necessarily the case. We might have found them to be 4 and 3 instead. What I'm trying to say is, there's 2 scenarios here. Either the pivot of A is smaller than the pivot of B, or the pivot of B is smaller. So these are 2 more sub-scenarios that we could consider. So let's summarize our scenarios. We said there's 2 possibilities. One is that the number of elements in the left chunks are bigger than or equal to k, or that they're less than k. In both scenarios, we might have sub-scenarios that either the pivot of A is smaller, or that the pivot of B is smaller. This makes for a total of 4 scenarios that we should consider. So let's consider them one by one. Thank you so much for watching the video. This is it for part 1 of the video. If you liked the video and would love to see part 2, please consider liking the video and subscribing to my channel. Making these videos really takes a lot of time, so I really appreciate all the support. Also, if you're feeling rather generous, I'll leave a link to my Patreon account in the description. So I'll see you in the next video.